This might be a good time to pause, slow down, look back at how far you have come on your journey through multivariable calculus. It has been such a long and wonderful journey, but there's a little bit more to go. From now on, we're going to be moving away from the three-dimensional world of X, Y, and Z up to field calculus in higher dimensions. This would be a fine time to stop, to say, that's it, I'm done. Green Gauss-Stokes, that's a perfect place for me to quit. But if you want to keep going, then let's see what's ahead. Now, the first thing you might ask is, look, do we really need to redo all of this stuff in arbitrary dimensions? I mean, it seems as though anything that's really physical would be in dimensions 2 or 3. Things like fluids or stuff like that. Well, let's think. There are some really good examples of fields in higher dimensions. One comes from dynamical systems. If you consider even simple-looking dynamical systems, they can have really complicated behavior. Why is that? Well, one of the reasons why is that a continuous time dynamical system, a vector field, often lives in a high-dimensional space where there's lots of room for crazy stuff to be going on. For example, this triple pendulum has 3 bars. These are described by 3 angles and 3 angular speeds. That's a 6-dimensional space that the dynamics is traveling through. That's pretty cool, and that kind of vector field is pretty high-dimensional. We have to work beyond 3D. Okay, let's keep going. Let's think about physics. If you want to do anything serious in physics, you're going to have to work in a 4-dimensional space-time, and you're going to have to work with fields of tensors, not just vector fields, but tensor fields as well. Now, that's pretty cool stuff. That's like, whoa. But even that 4-dimensional space-time is too simplistic for real high-energy physics. You start doing string theory, and even the simplest theories there have 10 or 11 dimensions that you need to work with. Keep going. If you think about probability, then all of a sudden you get to high-dimensional fields really quickly. There are things called Gaussian random fields that are kind of like random functions in space and time. Think about water waves, things like this. There are some really cool high-dimensional fields that show up in probability all the time. And if you really want to get high-dimensional, then start doing machine learning. If you look at neural networks, deep learning networks, things like this, then what you wind up getting is a very, very high-dimensional parameter space, where these parameters are connections between nodes in different layers. And what you wind up analyzing are gradient fields on these very high-dimensional spaces in order to optimize what that deep learning network does. That is super cool and super, super high dimensional. Okay, so you might be thinking, well, great, I like this. I want to do high dimensional field calculus, but how? How does this work? Well, let's think. You integrate one-form fields over curves, right? That's good. That's really helpful with things like vector fields. What comes next? We did 2-form fields, which you can integrate over surfaces. Okay, well, I can kind of see a pattern there, but it's not entirely obvious how we're going to extend all of this to higher dimensional fields on higher dimensional spaces. We're going to need something more, and what we're going to need is more math.